In this module, we focus on control system design, especially the root locus and also PID controller design. So I will introduce negative feedback control system, also PID controller, and how to use the root locus to study the stability of a P controller, and also evaluate the performance of the PID controller with different P and I and D components. And you're going to run the function of root locus and also know how to represent the PID in the Simulink. And these are the modules you should know before you watch this video. Especially you should know how to do Laplace transform, how to get the transfer function, and how to represent the model in Simulink. So in this module, I will show you one example, and for the controller design for blending system. So here is the blending system. So we have two input here. So this input right, we say maybe as the inlet flow 1, inlet flow 2, this 2 inlet, right, flow here. S1 and S2 and S are the mass fraction of component A, right? So we want to control X, right? We want to control the mass fraction of component A in the outlet flow. So what we're doing now is we measure here. So the AT means what is the composition analyzer. So we measure the mass fraction of component A, and then so this is what we're doing now. So we measure the component A, and then we compare the measure mass fraction of component A with the set point value. So E is the difference, right? It's Y, the measure output minus the set point value. We call this arrow. So based on the arrow signal, so here's the controller, right? The controller, we can control the valve flow rate. So GV is the valve, and then the valve we're going to control the flow rate, right? And then GP is the blender, right? So and then so the flow rate, you know, in the inlet 2, right? S2 equal to 1 means this inlet actually is the pure component A, right? So based on that, and then we control the flow rate of inlet flow 2, and then based on that we control the output mass fraction of component A. So this is the system, right? So the question we're going to study in this module is I will show you, hey, when we use different controller, for example, here we use different controller, for example KC, then you're going to get different output profile, especially what are the range of the KC values that can stabilize the system. That is the first question we're going to study. The second one is we're going to design different controller, right? P and PID controller. So we want to compare the performance of multiple controllers. So here is a brief introduction of feedback system. I believe you learned that from the process control or systems engineering courses. So the feedback control means what? We measure the output. So Y is the output, we measure the output, right? And then based on the measured output and then the set point value, and then we're going to control in this example is here we're going to control the opening of the valve, and then the flow rate of W2, the inlet flow rate, right? And then control the mass fraction of the output. So you can see this is a negative feedback. Why is negative feedback? Because we measure the output, right, and then compare the output to the set point value. So if the output is larger than the set point value, and then the system will push right, the output. So if the output is larger than the set point value, and then the system will going to we decreases the flow rate, right? Because the flow rate actually in the flow is pure component A. So to reduce because the mass fraction of component A is too high, so we need to reduce the mass fraction of component A. So therefore we need to reduce the inlet flow rate W2, and then we decreases the measure output, the measure mass fraction. So you can see the negative feedback means what? The system will change the output in the opposite direction. So for example, if the measure output is too large, and then the system is going to force the measure output decreases. That's why the negative feedback is important, right, to make the system stable, right? So the idea of the job of negative feedback controller is to reduce the measure output and with the set point value, so that we could keep the system stable. Okay, so PID controllers are the most commonly used controller, especially in chemical engineering. So we could get this KP, KI, and KD are the three corresponding gains. And the first one, E is what? ET is the measure output minus the set point value. We call this E. So we call it arrow, right? So this arrow represents the difference between the measure output and the set point value. So the first one represents the action of a controller on the base of the present arrow. So if the arrow is large, and then take more action, and the second one represents the action of the controller, right, based on the accumulation of the historical arrow, right, integration, right. And then the last one represents the action of the controller based on the predicted, so of course predicted arrow, right, because dt can be approximated by et plus 1 minus et parentheses divided by delta t, right? This will be t plus delta t. Okay, so we can predict the arrow in the next time point, right? So the idea here is the PID controller is try to push the system on the base of the arrow, right? So the current arrow, the present arrow, right, and then the accumulation arrow, and then the predicted arrow, right? So we have three terms here. So typically we present the PID control using this one, right? This is the nominal value, right? Control signal, right? And then this is the returns we represent here in parallel format, right? This for this one's KC. This should be KC over tau I. This one's KC times tau D, right? So tau I is the here the integral time constant. Okay, the KC times tau D. Okay, ES. So in Matlab, and typically we represent the PID controller in this extended, right, format here. Okay, so you just need to specify KC, KP, KI, and KD. Okay. Now I want to show you how to use the locus to represent to determine the range of the KC that stabilize the system. Okay, so you can see in the feedback loop here, so in this closed loop, right? So this the GV times GP times GM, actually they are the object for the controller to control, right? So we represent them here. So this we call, this is the control object. So we times them together, then we get this one, right? So so to determine the case so based on that, and then we get a KC, and then we get a closed loop system, right? And then based on that, we could get the root of the closed loop. And then we could plug here, so we could use the root locus command, right, to plug the root of the closed system. So we could get, so for example, we could get for different KC value, get the loops here, right here, and here. So if the root is negative, means stable, right? So this pink color regions of KC value system stable. Other than this, for example, for this part and this part, and the closed loop has positive root. So so this is positive root. So not, this means that the system is not stable. So based on that, we will select, right, good KC correct selection. Okay, now let me show you. So I'm going to build a new function, a new function here. Actually, we don't have no input function, right? So here I say main root locus. Okay, now let me type the system, right? This is the, so this is the open loop. Actually, we call open loop transfer function, right? This we call is open loop transfer function, for the controlled Okay, now let's type it in the Matlab here. Okay, now let's type it in the Matlab. So we see is clear means we clear all the variables. Right, as all the commands, CLC means clean the commands in the command windows. Then clear means clean all the variable in the workspace. Now represent the control object, right? In here we get 1 in the coefficient, right in the numerator, and then in the denominator the coefficient is 10, 11, 17, and 8, and 1. Okay, so after that, just use R as a locus, root, right? Locus, and then put 6. Okay, save it, and then run it. So here, right? So this the loop, right? You could clean it, and then you could get a game, right? This is the game. This is the KC, right? 2.61. They get a pose is negative. Okay, now you, for example, you could get the game just here, right? And if the game is larger than this value, and then you will get the you might get the positive pose, right? So tips, I will not show you to use a game larger than 12. Okay, so if for example if you get this one, you get larger than 12, so you're going to get positive pose, and the system is not stable. Okay, now I want to show you how to represent. As I mentioned, right? We could represent the PID controller and in Matlab. Okay, so now so we know the KP controller and PI controller and PID controller. Now we just need to type in the in Simulink. Okay, now let me. Okay, so we're gonna have a new. So here's new blank model, right? And then I will save it. Right, I'm gonna build a Simulink model for PID controller. PID Simulink PID controller. Okay, now we could represent, see here. So what we can do is we're gonna represent this closed loop system in so this closed loop system here in Simulink, and then we change the controller parameters, and then we plug, and then we do summation, and then we could compare the output for different controllers. So here's what we get. So you can see this right, this should be GV, GP, GM. This would be GC, right, for P controller, PI controller, PID controller. And then the set point value, right? This set point value. Then this measure output, right? So now let me see. The question is, we're going to have a step change in the set point value, and then for 100 minutes, right? We want to compare the performance of P and PI and PID controller. Okay, now again so you could limit now let me show you, right? Here, so for the PID controller, you're going to get this KC, this is the KI, this KD, right? Okay, so we will get KI actually is a KC over tau I, right? Because I did not give you the KI, right? I give the tau I, so you can see. So KC over tau I is equal to ki, right? So kc times tau d is kd. This. So in Matlab, you just need to input kc, ki, and kd. So in Matlab, you need to input kp, ki, and kd, right? And then this one's kc, this ki, this kd. Now I want to show you one example how to build a PID controller in Simulink. Actually, we could find the PID controller module in the library of Simulink, especially in the continuous category. So before I show you how to import the PID controller parameters, here are the parameters, right? We take from the example. So again, when we build the PID controller, so for example this PID controller in Matlab, and you could pick like what type of controller we use, like PI, PID, PD, and PNI. And also you could input those parameters here, but be very careful. These parameters, this first one is what is KC, the second one is KI, and the last one is KD. So here's KI actually is equal to KC over tau I, and KD equal to KC times tau I, right? So we don't input the tau I and tau D, we input the KI and KD. So KC is the same as the one right here. Okay, so therefore you need to calculate, for example here, right? Calculate the KI first, like KC over tau I, and then this one is KD, so it's KC times tau I. Okay, so tips, the coefficient n is a large recourse filter, right? So you should run this from the process control class, the filter, and tips is a large value. 100 should be enough. Okay. Now so here is what you should get in Simulink. Now let's work together and then type this 3 feedback loops into the system. So you go to the Simulink, and then you can add a new model, right? And then save it. So I would say is PID controller, right? So first, so we're going to get the transfer function, right? This transfer function, and so let's go back to the example here, right? This transfer function for the valve, and then transfer function for the blending tank, and then the transfer function for the measurement component. So this one is GV, this GP, and this GM, right? So they are given. Okay, now let's get this the first feedback loop first. So I'm going to get a transfer function, right? So transfer function in the continuous, and continuous, and then you're going to get should be transfer function here. Okay, and then so we have how many? 1, 2, 3. So we get 3 copies of transfer function. So just hit the control key on the keyboard, and then you draw it, and then you can make a copy. So for this one, we're going to flip it. So you get to go your right click and the mouse, and then you get here the flip block, and then you link them together. Okay. So now let's type the value. So the first one here should be, right, the numerator is 1, the denominator should be 2s, so the coefficient should be 2 and 1, and then for second one this should be 5 and 1 in the denominator, and then for the measurement 1 is 1, right? 1 over s plus 1. So this was done, and then we get a PID controller here. So we go to continuous and then PID controller, right? So link them together, but here we only have P controller, so you double click and then you click P controller, so you select P controller, and then and then you need to put the number of the parameter of KC. So KC equal to what? KC 1.6 here, right? So for the P controller, KC equal to 1.6. So we're going to go back here. This is equal to 1.6. So we're done with the P controller, right? And then after that, we going to get the comparator and the support value, right? So the comparator actually is here. It's a subtraction right here. So get this one, and then support value. Remember the support value here is a unit step change, right? So this is unit. This is unit step change. Okay. So we're going to go to the mask and to get the module of the here for the comparator. Here, subtract here. Put here. Link it, and then link this one. And then now let's go to the sources to get the step input. So this step is unit step. So unit step. So we go check step time. Maybe it's 0. And then the final value is 1, right? So we're done with the P controller. Okay, so similarly we'll get the PI here and PID controller, right? So we just copy and paste, right? Control C, and then you're gonna Control V, right? 2 times. So Control plus V 1 time. You draw them together, make it look nicer and neat. Another one is Control here. Okay. And then so we're gonna change this one to the PI controller. Let's take a look at the parameters of the PI controller. So we get here, double click. Okay, now let's double click the P. This one is PI controller. So we select PI. Right, and then the KC is still 1.6. Remember KI, right? Remember KI equal to what? KI equal to KC over tau I. So we have tau I is 6.15. So okay, KC is equal to 1.6. Then tau I is 6.15. Okay, so we're done with the PI controller. Now let's do the PID controller. So PID controller, double click here, and then you select PID controller, and then again you need to type the value in here. So again you get KI equal to KC. KC now here, be careful, KC now change it, right? It's 2.46. So the KC 2.46 over tau I. Tau I here is 8.03. 8.03. So to calculate KD, you could know the KC times here. KC this should be tau I. This should be tau. This typo here. This should be tau D. Okay, tau D. So you get KC is right 2.46 times tau D. Tau D 0.67. Okay, so we're done with the PID controller. So we already typed PID controller, and then right, save it. And so to get the profile, we just save the data, right? The output. So at the same time, we also need to put time variable here. So we can get the sources here, get the time, clock, the clock here, the clock, and then we save the data. So here we save the time in t, and then the result from PI controller is y1, from PI controller is y2, and then for the PID you get y3. So you're going to get the sinks and then workspace, alright, and link it, and then double click, change the name of the variable to t. So be very careful, right? When you set up the variable, you also need to set up the format, and here we use array, so be careful, you need to use array, okay, and to plot the result. So similarly, we're gonna get a workspace here to recall the result from the PI controller, right? So this is y, so we get y1 here, right? So we get y1. Again, you need to change this one to array, okay, and so similarly you could do that to y2 and y3, and you could just make a copy, right? This copy, and then this copy, change this one to double click, it's to y2, again it's in array, right? Link it, and you can see this solid point here means these two lines, they are connected, right? The last one here should be y3, save it, and then alright, and then save it. Now let's take a look how long we should do the simulation, right? The simulation, let's go back here. The simulation unit step change for 100 minutes, so we're going to do 100 minutes, right? So we change this one, the time to 100 minutes. Okay, now we save it, and then you can run it. Everything should be, hopefully it's okay. Then now we could type this command. You could save the commands in a document, or you could just type it in the. So for example, I save. For example, I will going to save it, right, in a document, and then we don't need to type it in the command window again, right? So this ty1, again this plans it together, and then you get this is a red color, and this one is a light bit. Okay, then you want to save it. So plot main plot PID. Okay, then you can hold on. Then you can plot simulate plot. You just copy, right? Copy and paste. Copy and paste. Paste. But you need to change this one to y2, and the colors is B, is be y3. The colors should be black, is K, and then delete this, hold on, and then you get S label. And here you get time. Let's put minutes here, and then this one you get. We change the font size to 12. So similar, you get Y label. And here output is Y, and then this font size, right? And then we also need to show which one's for P and which one for I and which one's PID, right? So we're going to add a legend. Add a legend here. Legend. So the first profile is for P controller, right? And then we could copy this one, P controller, the second one PI controller. Copy. And this will be PI. The last one is PID. Just save it. Then run it. So this is the profile you should have, right? Okay. So you can see for the P controller. So this is set point change, right? This is set point change command. Use green color. This set point change command here, right? This set point change, and you can see, and for the P controller, there's an offset here, right? Offset means the the change of status state value, right? So this the status value we should have, right? This is set point, right? But this is what we get from the controller, right? So after we put the controller in, the output is not equal to the set point value, so we call this offset. As you can see, if we just use P controller, we going to have offset in the output, right, of the system. If we use PI and PID, and then and we don't have. So if we had I component here, we have I component here. So but PI or PID, we don't have offset. And also you can see PI controller here. PID controller actually is faster, right, than PI, right? Because we had the D component here. The D component can help to make the system respond faster. Okay, so we are done with the control system design and PID controller.